In this video, we'd like to take a look at the limits as x approaches positive or negative infinity of rational functions. Rational functions are just functions that are the quotients of polynomials. We looked at polynomials in the last video, and what we would like to remember here is that as we look at and I should have inserted here small enough. The idea of the limit at positive or negative infinity is that if the values of f can be made as close as we like to L by taking large enough in the case of positive infinity, small enough in the case of negative infinity, values of x, then we write the limit as x approaches positive infinity of f of x is L, or the limit as x approaches negative infinity of f of x is L. And this also determines the end behavior where the asymptotes are. Okay, all right. Also recall that we have all of these linear properties. The limit of the sum is the sum of the limits, and the limit of the difference is the difference of the limits, and so on, just as before with all the other limits, that these have happen as x approaches positive or negative infinity. So now I'd like us to remember the general statement that we had way back, all right, from the first the video on basic limits, all right, that the limit as x approaches either positive or negative infinity of c over x to the n is 0, assuming I should really say here that n it has to be like 1, 2, 3, 4, or so on. Okay, it has to be a positive integer. All right, and what we want to do is I want to look at the limits of rational functions. Now, we're looking at the limit as x approaches positive infinity. Now, by the way, again, the mistake I see students make over and over again on exams is that they try to apply this technique when x is approaching 5 or some other finite value. This technique only works when x is approaching positive infinity or negative infinity. So let's take a look at this. The limit as x approaches positive infinity of 3x to the fourth minus 4x to the third plus 2x minus 5 over 7 plus 8x to the third minus 15x to the fourth. Okay. And if we look at this, what I'll do is I'm going to take your book and textbooks sometimes take the highest power overall, but I've found that it's helpful if we take the highest power in the denominator, and in this case that is the highest power overall. And what we're going to do is, so the highest power of x that appears in either the numerator or denominator, but basically look at the highest power that appears in the denominator is x to the fourth, and I'm going to multiply this rational function by 1 over x to the fourth, the reciprocal of that highest power of x, over itself. I do it that way so that I'm multiplying by 1. All right, if I do that, remember that you have to distribute, so I'm going to have to multiply each term in the numerator and each term in the denominator by 1 over x to the fourth. So when I multiply 3x to the fourth times 1 over x to the fourth, I just get 3. When I multiply negative 4x to the third by 1 over x to the fourth, x to the third cancels, and I'm left with negative 4 over x squared, or I'm sorry, 2x times 1 over x to the fourth. I'd get a 2 over x to the third, and a minus 5 over x to the fourth is what I'd get where the last term is. In the denominator, I'll get a 7 over x to the fourth plus 8x to the third over x to the fourth is 8 over x minus 15x to the fourth over x to the fourth is 15. And now if I take the limit as x approaches positive infinity, all of these terms, except for the 3 and the negative 15, all of those terms are of that form c over x to the n, and so they all go to 0. So this limit is going to be 3 minus 0 plus 0 minus 0. I'll just put in the plus and minus signs. It doesn't, of course, matter whether you add or subtract 0. All right, and then I'd have in the denominator, I'd have 0 plus 0 minus 15. So that's going to be 3 over negative 15. That's a negative 1/5. So that would be this limit. Notice that the rule, take it, the technique, take and divide the numerator or multiply the numerator and denominator by the reciprocal of the highest power of x that appears in the denominator. Here's a graph of this function. Now, by the way, these lines here shouldn't really be there. All right, there's something going on down here, and the graph is just trying to connect points. But notice the end behavior. The end behavior. All right, as we go off to the right, and in this case, as we go off to the left, all right, this function appears to be approaching point 2, which is 1/5. And so we have a horizontal asymptote at y equals 1/5. All right, that limit as x approaches positive or negative infinity will give us the horizontal asymptote. Let's take a look at this one. All right. Okay, so you can guess what we'd multiply by here. This is the limit as x approaches negative infinity of 7x squared plus 9x minus 1 over 3 plus 2x squared. Look at the highest power of x in the denominator, and we'll multiply the numerator and denominator by 1 over x squared. And if I do that, this will become the limit as x approaches negative infinity of this 7x squared times 1 over x squared is 7 plus 9x times 1 over x squared is 9 over x minus 1 over x squared, right, all over 3 over x squared, right, plus 2. And again, as x goes to negative infinity, these terms that have x's in the denominator all go to 0. So we're just left with 7 halves, which is 3.5. And here again is this the graph of this function. Notice at the endpoints we have the function approaching 3.5 or 7 halves, and so this, as we approach negative infinity or positive infinity, by the way, so we have y is equal to 7 halves is a horizontal asymptote for this function. Okay. Let's take a look at this one. All right, here we have the limit as x approaches negative infinity of 1 plus 5x over 4x squared minus 2x minus 1. All right, the highest power of x in the denominator is 1 over x squared. So I'll multiply by 1 over x squared divided by 1 over x squared. And that's going to be equal to the limit as x approaches negative infinity of, multiplying this out, I'll get 1 over x squared plus 5 over x in the numerator, 4 minus 2 over x minus 1 over x squared in the denominator, and all of these terms with an x in the denominator are going to go to 0, so this will become 0 plus 0 over 4 minus 0 minus 0, which is 0. Okay, 0 over 4 is 0. So notice that this thing goes to 0. By the way, you realize that will happen if we have the leading term in the denominator has a bigger degree than the leading term in the numerator. The highest degree term in the denominator has a bigger degree than the highest degree term in the numerator. Here again is the graph of that. Notice in this case we have, as we go to positive infinity or negative infinity, all right, this graph is approaching y equals 0, and so y equals 0 is going to be a horizontal asymptote for this graph. All right. Well, again, we should sort of expect the same thing here because we have a higher degree term, leading term in the highest degree term in the denominator has a bigger power of x than the highest degree term in the numerator. But we'll go through you should be able to go through this work anyway. We'll multiply by 1 over x to the 5th in the denominator and in the numerator. And this will become the limit as x approaches negative infinity of 4 over x to the 5th minus 3 over x to the 4th minus 5 over x to the 3rd plus 3 over x squared, and in the denominator we'll have 1 over x to the fifth plus 5 over x to the fourth plus 5 over x to the third minus 5 over x plus 3. And now as x approaches negative infinity, all of these terms where x is in the denominator go to 0, so we would have 0 over 3, which is of course 0. And notice we expect y equals 0 to be a horizontal asymptote for this. Notice as x goes to negative infinity, the y value goes to 0. Y equals 0 is a horizontal asymptote for this function. Let's take a look at another example. All right, in this case, we have the limit as x approaches negative infinity of 1 plus 2x minus x squared over 4 minus 3x. The highest power of x in the denominator is 1 over x. So let's multiply this by 1 over x divided by 1 over x. If we look at this, all right, this is going to be the limit as x goes to negative infinity of 1 over x plus 2 minus x squared divided by x is x, right, all over 4 over x minus 3. Now, as x goes to negative infinity, notice the denominator is going to 3. The numerator is going to 0 plus 2, all right, plus infinity. Remember, negative x looks something like this. All right, okay, so this thing is going to be, because this term is going to positive infinity, it's the highest power of x, this will go to positive infinity. All right, let's take a look at this. Oh, I'm sorry. This would be like, I forgot about the negative 3 in the denominator. It would be like negative 2/3 plus x over 3. And so that would, x over 3 would be like this. All right, so x will go to negative infinity. My mistake, sorry about that. All right, and notice x is going to negative infinity. Notice in this case there are no horizontal asymptotes. All right, and we can see that that's going to happen. We're going to go to positive or negative infinity when the highest degree term in the numerator has a bigger power of x than the highest degree term in the denominator. Okay. All right, this is how we take the limits as x approaches positive or negative infinity, but not any other value, not x is equal to 7, 5, negative 2, or anything like that, all right, of rational functions.